Okay, so the last part of today. So you see that the background changed because we are not strictly talking about geometry anymore. We are talking a bit about probability distributions. Okay, so statistical manifold is something which is more complicated than what I'm going to define. So we give you an intuitive idea, which is completely wrong, but it suffices for what I'm going to say. So we take a k-dimensional manifold, and let's say that we call it a statistical manifold if we use it wisely, in a way, to parameterize a set of probability distributions over some domain X. Therefore, for every, I will call it theta because P will be for the probability, theta in M, we will have a corresponding probability distribution on X, which will be P theta of X. Now, for example, you can take the space of one-dimensional normal Gaussian distributions. You can parameterize it in a lot of ways. So you can parameterize it, you can associate every distribution to its mean and its variance, or its mean and its standard deviation, or its mean and its precision, which is just the inverse of the variance, standard deviation, one of them. I don't remember. And so different parameterization give different charts of the manifold, but the manifold, so the set of all one-dimensional normal distributions, is the same. Now, let's talk a bit about we can tell apart probability distributions. So let's say we have a discrete probability distribution and we draw n samples from that probability distribution. We can estimate the probabilities with the frequencies. It's just common. And the probability for the frequencies is given by a multinomial distribution, which, if you take a lot of samples, is a Gaussian, that is proportional to a Gaussian. There is a coefficient, so I don't have a right, which is of this form. So the Fj are those observed frequencies, the Pj are the probabilities, and you get this thing. Now, suppose you are trying to decide if the probability on your space is one or another. So is P or P bar. When can you tell it? Well, if you draw enough samples, this is the probability for them. So if you have two different probability distributions, the frequencies will go toward one or the other if you're trying to tell them apart. So observe the minus here. So in the end, if this function calculated on the two probability distributions is very small, this means that the exponent without the minus sign is very large, so the differences are big, and so you can tell them apart because this distribution will go toward one or the other, so these will remain big because these differences will go to zero, hopefully at some point. So we consider this quadratic form, the exponent, as some sort of, I mean, it's called distinguishability distance. It's not a distance because if you exchange P and P bar, you get another function because, I mean, the numerator is symmetric, but the denominator is not. So. But it's called, many times these are called divergence measures. They are not divergence in the sense of calculus, they are just measure of how much two probability distributions diverge. And anyway, so they're called distances, they're not distances, they're called divergences, they're not divergences, but that's it. If you pass to the continuous case, if you take not really the limit, but if you do sort of the same reasoning on the continuous case, this time, in terms of the parameters, I don't want to be very specific on this. You end up with this thing which is really similar to the other. Now, the expected value of this quantity vanishes identically. Not really of this one, of the, of the limit of these for theta prime going to theta. But anyway. So you can say the variance of the limit of this thing, and you get a metric, because the variance gives you a symmetric matrix, GAJ, which is written like this. So it's the integral over x of p theta of x, the derivative in theta I of logarithm of p theta, times the derivative in theta j of logarithm of p theta. This is called Fischer information metric. And so it's an infinitesimal version of the distance between two probability distributions, of a distance, but not really a distance, of a measure of distance between two probability distributions, of a divergence. So the distance, the divergence is not symmetric, for example, but its first order vanishes, so you take the second order expansion, which is symmetric, so it's a Hessian, and you end up, you discover its positive definite, and so you end up with a metric. And this is called the Fischer information metric. Now, it's not only related to how much two probability distributions are far, but also to the relative entropy, which is this concept. The relative entropy is dysfunctional, which I don't care too much about. It measures the information lost if we replace one probability with the other. What do I mean? You take samples from a probability distribution, and you have an encoding algorithm that it's optimized on that probability distribution. So it can encode the samples of that probability distribution very, very well with very, very few bits of memory. Now, what happens if you take the samples of one probability and use the codec of the other? You will use extra bits, okay? So this loss in efficiency is the relative entropy between the two probability distributions. Obviously, the roles of the two probability are different. One is the one you use to draw samples from. The other is the one you use to define the codec on which you encode the results. So if you exchange them, no one guarantees that the relative entropy will be the same, and in fact, it will be not. So the divergence D, the relative entropy, this operator D, is not symmetric. Now, this D has also another name, which I never remember. Is called the divergence of I don't have it here, and I don't. Kullback-Leibler is the Kullback-Leibler divergence. Now you're happier because you know this is a very important piece of information. But anyway, it measures the information theoretical distance between the two probability distributions. Now, it is positive definite and is zero only if they coincide. So the Taylor expansion at theta equals theta prime begins with the second order terms. So we can take the Hessian matrix, perturbing theta prime with an eta, writing theta prime as theta plus eta, and you end up with this formula, which is the same. So the Fischer metric is also the Hessian part of the relative entropy, so of the Kullback-Leibler divergence. Now, actually, take a reasonable f on your space where you have your probability distributions. If beautiful D is any way to measure the difference, distance, divergence, whatever you want to call, between probability distributions, then it should abide the principle of information monotonicity. That is, if you take two probability distributions and you measure their dissimilarity, then you precompose both probability distributions with your f, which is a transformation of your space. Then you cannot really improve their distinguishability. So you cannot tell them apart better. You have worsened things. If you wanted to tell them apart, to see the difference between them, shuffling things on the domain made things worse. Or at most, they stayed the same, but usually it made things worse. Too much. Now, any measure of divergence that obeys information monotonicity principle gives rise to a multiple of the Fischer metric as a Hessian. So it has to be vanishing first order, and the second order has to be the Fischer metric. So in a way, every reasonable way to measure the difference, the distance between two probability distributions gives you the Fischer metric. That is why the Fischer metric is usually put on statistical manifolds. So a statistical manifold is a manifold of probability distribution with the Fischer metric, actually. Now, you have a metric, so you can do the Riemannian gradient descent. Given a statistical manifold with a Riemannian metric, which is the Fischer metric, so this sentence is badly written, we can implement the algorithm of Riemannian gradient descent once we define a suitable retraction. And there are ways of defining retractions on outside manifolds. We'll talk about that later, but you can do any retraction you want, actually. So if J is the functional to minimize, the update rule, so the step of our algorithm is this one, no? Which is, in our musical notation, this one. In coordinates, we are just raising the index. So we have these where no. This is 1 over f. So f minus 1, it's better. Anyway. You suggested, I lost track of the chat, so I just saw that you prompted me with the name Kullback-Leibler. Yes, I was searching it on the notes I had on the other computer. But anyway, this is 1 over f. So because this is the inverse metric. It's the metric with the upper indexes, so it's the inverse of the metric. So it's 1, usually written 1 over f, is the inverse of the Fischer matrix. Anyway, a common application of this is to find or approximate the choice of parameters that maximize the likelihood of some data or something like that. Another common application is to use this for statistical learning. So if you want to, your system to learn a probability distribution. Now, another interesting application is the following. Suppose you have a function you want to maximize or minimize on a finite set. You cannot use analytic methods, calculus, gradient descent, whatever, because the set is finite. So you have a number of objects, and you have a function on those, and you want to find the minimum, like the strings of an alphabet or something like that. It's not I mean, you cannot apply all the procedures the procedure we talk about, which was the Riemannian gradient descent or the gradient descent. You can transform it, however, in a continuous problem with probability distributions. We define a family of probabilities parameterized on some open set in Rk. And they are called search distributions. So each one corresponds to a different way to search for the minimum, focusing on different parts of our set X. So every probability distribution gives different weights, different masses, to every part of X. So what is the minimum of our function f on X? Well, is the minimum of the expected value of f of X with respect to p with lambda. If you find the minimum of this functional, which is a functional now on Rk with which is a statistical manifold, you find the minimum of f. It's intuitively, I hope it's clear, but you can also prove it, and it's not that difficult. So now you have to minimize j on Rk. The nice thing is that you have empirical method, meaning from samples, to estimate, to approximate the gradient of j and the Fischer information matrix. So you can, the gradient, the differential of j and the Fischer information matrix. So you can write down the Riemannian gradient of j with not too much computational cost. Okay, the function j clearly is a bit difficult to differentiate explicitly. But you can use the log likelihood trick. But anyway, yes. And also the Fischer information matrix, so the matrix of your Riemannian metric can be approximated by empirical observation. An application of this, really nice, I think, is compiler optimization. So you have some code which has to be compiled, programming language. You can apply some transformations and keep on X. You keep the same input and the same output, so the code does the same thing, but you change the running time. So, for example, you unravel some loop, or you rewrite some array operation, stuff like that. Huh? You can improve or worsen the running time. Now, let S of X be the set of admissible transformations, so the ones that don't change the input and the output of your algorithm. And f of X and S is the running time of X transformed with S. Now, you are interested in finding the minimizing transformation, so the way to compile your code that minimizes the running time. Obviously, this in principle depends on your code. Given a precise piece of code, you can devise a way of compiling it that minimizes the running time. So you're actually interested in transformation. So what you want to find is the argmin for S in S of X of the running time. Now, here. Now, an interesting thing. You could think about this. You are given a set of solutions for some pieces of code. You have the x1, x2, xn pieces of code, and you know s1 star, s2 star, sn star. You would like to learn how to find good solutions. There are many approaches. One approach is to define a probability distribution qs condition to x on good solutions, which gives high probability to the best solution. Learning Q, so being able to reproduce Q, knowing just the solutions for x1, xn, so the expected values, is an optimization problem on statistical manifold. So it is this kind of problem. But I mean, it's not the only problem formulated like this. There are a lot. And in general, in machine learning, you have, this is a machine learning problem actually, but in machine learning you have a lot of statistical gradient descent you can apply around. Now, the last couple of things which are really, really dense. Consider a statistical manifold with a Fischer information metric. So you have your manifold, the Fischer information metric G. Two connections are said to be conjugate if their covariant derivatives satisfy these, well, are torsion free and satisfy this relationship. Maybe, let me think for a second, I don't want the, yeah, I don't, yeah, I don't want the chu. I don't know why there's a chu here. Checked, but this relationship. So it's more or less the compatibility condition, but you use one connection here and the other connection here. One covariant derivative here and the other covariant derivative here. Given a connection, torsion-free connection on a Riemannian manifold, there is a unique conjugate connection. And the Levi-Civita connection is self-conjugate. Now, take any divergence measure on probability distribution. So, you have, for example, the Kullback-Leibler or the distinguishability measure we talked before. There are a number of other distances, measures, whatever you want to call them, that you can define. And so take any of them. Typically, they are not symmetric. So you have that the distance between theta and theta prime is not the distance between theta prime and theta. So you have these. Now, you can define conjugate connections by specifying their Christoffel symbols. So how much they differ from the partial derivatives with respect to coordinates, employing the asymmetry of the divergence you want to use. So now, this is a bit ugly, but okay, ignore the metric here, which you need only to put an I up there, but you could write the I downstairs, it's the same. So we're taking here the derivative, the partial is the derivative with respect to the first set of variables. The partial prime is the derivative with respect to the other set of variables. So clearly the difference between the two is that you exchange the roles of theta and theta prime. Okay? So, and by the way, also G, which I've written here, but G is again given by the derivatives of D. So you remember, if D is a divergence measure with respect to the monotonicity information property principle, then the Hessian of D will give you the Fischer metric up to a number, up to a constant. So in the end, you are writing everything in terms of the partial derivatives of D. Now, having an explicit formula, it's not difficult to show that these two connections are conjugate. But the main fact is, I mean, it would be not enough, this, to show that they are conjugate. The main point is that in the formula, let's see it again, you have also the metric. So you have the two connections and the metric. But here, also the metric is given in terms of partial derivatives of this divergence function. Now, a technical point, but I really don't want to enter into this, but for any two conjugate connections, you can take the differences between their Christoffel symbols. And you will find always the same thing, which is a 3-index monster, totally symmetric, in every pair of indexes. And technically, a statistical manifold is a Riemannian manifold with a 3-tensor defined that way. And then from there you get the Levi-Civita connection, and you can alter the Levi-Civita connection to get conjugate connections. So you sum a part in the Christoffel symbols, or you subtract a part in the Christoffel symbols, and you find these connections. Now, what's the point? The point here is that you can perform these constructions with different divergence measures. I've mentioned you two divergence measures, so the distinguishability distance and relative entropy, but there are a number like Bregman divergence and other stuff. I've told you that the metric you obtain is always the same up to a factor, so it's actually always the same, but the connections you obtain are not always the same. Because here, you don't only have the derivatives in one, you have the derivatives, two derivatives in one variable and one in the other. When you calculate the metric, you only take derivatives in one variable. So these two quantities here will, in principle, change wildly when you change D. If you take the distinguishability measure or the relative entropy or the Bregman divergence, you have different statistical manifolds with more or less the same metric, but different connections. So in the end, different objects. Now, on these pairs of connections, you can study a lot of stuff, like, well, we will see what it is, but curvatures or geodesics or stuff like that, and they all have interesting interpretations in terms of the probability structure that you have underlying. Moreover, here we define two connections which are conjugate, but we can interpolate. We can interpolate between them, and in the middle, so the mean of these two connections, so one plus the other halves, so you take the covariant derivatives, you say nabla plus nabla star halves, this is the Levi-Civita connection, the Levi-Civita covariant derivative. But any other combination will give you a connection, and if they are opposite with respect to Levi-Civita connection, they are conjugate. And okay, this sentence is not so informative, but you can study a lot of properties related to these conjugate connection. Also, you can use both to do Riemannian gradient descent, obtaining what's called mirror gradient descent, which is a bit weird, and do many other weird things, which I won't be entering too much. Last thing I want to mention, I won't be taking the full 45 minutes, obviously. The last thing I want to mention is a nice idea, more or less. So, in Bayesian statistics, but sometimes you want to pick parameters randomly. So you have your p theta, and theta varies in M. Now, sometimes, for example, for Bayesian statistics, you want to select parameters randomly. That means in an, let's say, unbiased way. So technically, you want to design an uninformative prior distribution for Bayesian inference. So it means you want to select some thetas, and the probability distribution on M with which you select these thetas shouldn't be interfering with what you want to do afterwards. So it should be uninformative. How can you do that? Well, the first thing you could think of is the uniform distribution on M. What does it mean? Well, M many times is a piece over N in statistics. So you can just take the Lebesgue measure, the K volume. But this doesn't really work. Also, it depends on the parameterization. For example, take the example from the beginning. You have one-dimensional normal distributions, and you can parameterize them with mean and variance, or with mean and precision. Now, the uniform measure on mean and variance and on mean and precision are quite different one from the other, so it's not the same. Now, one thing you can do is this. Given G, the Fischer information metric, given a metric, you have a distance, so you can define a volume. Which in coordinates is the square root of the determinant of the matrix in local coordinates. Maybe we'll be talking about that, maybe not in some other lecture, but you can define a volume on M. So you can define, you can draw samples from the parameter space, giving equal probability to equal volumes. And this is what is called Jeffrey's prior, I think. So your probability of theta, of the parameter theta to be chosen for a Bayesian inference, for example, is proportional to the square root of the determinant of the Fischer information matrix. And that's another, this is called, yes, Jeffreys prior, I think. And this is a way to obtain uninformative prior distributions on the parameter space. And again, is another application of this Riemannian setting on statistical manifolds. And I think I will stop here.